You flip a switch, and the light turns on instantly. Simple, or so you think. Most people believe electricity rushes from the power plant to the bulb the moment you press that switch. Richard Feynman said that idea is completely wrong. The electrons didn't race through the wire. Nothing was used up, and the real energy never even traveled inside the wire. In the next few minutes, we'll break one of the most common myths about electricity. And once you understand it, you'll never look at a light switch the same way again. Most people grow up believing that electricity is something you use up. You turn on a light, electricity flows into the bulb consumes it, and whatever is left disappears somewhere down the wire. It feels natural to think this way because we're used to everyday substances being consumed. Fuel burns, batteries die, and food vanishes when we eat it. So our brains automatically place electricity in the same category. Richard Feynman loved attacking this kind of thinking, not because it was stupid, but because it was lazy. It stops curiosity at the exact moment when real understanding should begin. In reality, electricity itself is not consumed at all. What flows through a wire is electric charge, usually in the form of electrons. And those electrons are not destroyed inside your devices. They don't vanish in a flash of light or dissolve into heat. They continue to exist before, during, and after the circuit is operating. When you switch something on, you're not sending a supply of electrons to be eaten by the bulb. You're setting up a continuous motion of charges that already fill the wire. Feynman often pointed out that the confusion comes from mixing up current with energy. A light bulb uses energy, not electricity. The current, the movement of charge, simply provides a way for energy to be transferred. If electricity were actually used up, the wire coming out of a device would carry less charge than the wire going in. But measurements show that the same amount of charge flows into a device as flows out of it. Nothing is missing. Nothing has been consumed. Think of it like a loop of people passing a ball around a circle. The ball represents energy, and the people represent electrons. The people don't disappear when the ball reaches them. They pass it along. The bulb doesn't eat the electrons. It takes energy from the electric field and converts that energy into light and heat. The charges keep moving, endlessly circulating through the circuit. This is why the idea of electricity being used up falls apart the moment you think carefully about closed circuits. In a complete loop, charge cannot simply vanish. Nature doesn't allow that. Charge is conserved, just like mass and energy. Feynman emphasized this conservation because it exposes how misleading everyday language can be. When people say a battery runs out of electricity, what they really mean is that the battery can no longer maintain the electric field that drives the current. The electrons are still there. The wires are still full of charge. What's gone is the battery's ability to push energy into the system. Even the word current tricks us. It sounds like a stream that flows in and then drains away. But current is just a rate, a measure of how much charge passes a point each second. It tells you nothing about consumption. The same current flows everywhere in a simple circuit. If electrons were being used up along the way, the current would decrease as you move down the wire. It doesn't. Feynman's deeper lesson wasn't just about electricity. It was about how easily we fool ourselves by borrowing familiar metaphors and never checking whether they actually fit reality. We accept the phrase, "whoosing electricity," and stop asking questions. But the moment you ask, what exactly is being used? the myth collapses. Not charge, not electrons. Only energy, energy transferred, transformed, and conserved. Once you let go of the idea that electricity is consumed, everything starts to make more sense. Circuits become logical systems instead of mysterious pipelines. Devices stop being black boxes that swallow power and start becoming places where energy changes form. And that, Feynman would say, is the difference between knowing a word and understanding a thing. A common picture people carry in their heads is that when you flip a switch, electrons take off running, racing through miles of wire from a power plant to your home, crashing into a bulb and making it glow. It's a vivid image, and it feels intuitive. Richard Feynman loved pointing out that intuition is often the most dangerous guide in physics, because in this case, the picture is almost entirely wrong. If electrons actually moved through wires at high speed, the world would behave very differently. You'd flip a switch and then wait, and wait, and wait some more. The reason is simple. Electrons in a metal move astonishingly slowly. Their average drift speed in a household wire is often measured in millimeters per second. That's slower than a crawling insect. At that speed, electrons coming from a power station would take days or even years to reach your light bulb. Yet the light turns on instantly. That single observation already destroys the myth. Feynman emphasized that what turns the light on is not fast, moving electrons, but the rapid establishment of an electric field throughout the circuit. When you close a switch, you change the conditions of the entire system. The electric field adjusts itself almost at the speed of light, and the electrons already present everywhere in the wire respond together. No long distance race is required. The wire was never empty. It was always full of electrons. Switching on the circuit doesn't summon new electrons from afar. It nudges the ones already in place. Each electron shifts slightly, bumping its neighbors like a tightly packed line of people, where a small push at one end is felt immediately at the other. The individuals barely move, but the effect travels fast. This is where everyday analogies break down. We imagine motion as objects traveling from one place to another. But in electrical systems, the important motion is collective, not individual. The signal moves fast. The particles move slowly. Feynman loved this distinction because it exposes how misleading our mental pictures can be when we cling too hard to them. Even in alternating current, where electrons oscillate back and forth instead of drifting in one direction, the myth persists. People still imagine electricity coming from somewhere far away. In reality, the electrons mostly wiggle in place. What changes is the electric field driving that motion. Energy is transferred through the field, not by electrons flying across the country. This misunderstanding is why people are shocked to learn that cutting a wire doesn't drain electricity out of it. The electrons don't spill onto the floor. They remain in the metal, exactly where they were before. The wire still contains charge. What's missing is the organized push, the field that makes their tiny movements useful. Feynman often warned against confusing cause with carrier. Electrons are the carriers of charge, but they are not the cause of instant action in circuits. The cause is the electric field, set up by charges and boundary conditions throughout the system. Once the field exists, the electrons respond locally, and the effect appears everywhere almost at once. Understanding this changes how you see technology. It explains why signals in cables can transmit information at near light speed, even though the particles inside crawl. It explains why energy delivery is not about shuttling particles over long distances, but about maintaining fields and relationships. And it shows why the phrase, "electrons rushing through the wire," is more poetic than true. For Feynman, this wasn't just a correction of a detail. It was a reminder of how physics really works. Nature doesn't care about the stories we tell ourselves. It obeys laws, and those laws often contradict our gut feelings. The moment you accept that electrons don't race through wires, you take a step away from comforting myths and toward actual understanding. One of the most surprising ideas Richard Feynman emphasized is that the energy in an electrical circuit does not actually travel inside the wire itself. This sounds almost absurd at first, because the wire is the most visible part of the system. We hold it, we connect it, we watch current flow through it. So it feels natural to assume the wire is where the energy lies. But Feynman delighted in pointing out that the most important things in physics often happen where we're not looking. To understand this, you have to separate two roles that are usually mixed together in our minds. The wire provides a path for charges to move. The energy, however, is carried by the electromagnetic field that exists in the space around that wire. The field is not a vague mathematical trick. It is a real physical entity, storing and transmitting energy and momentum. When a circuit is operating, energy flows through the field surrounding the conductors and into the device, not along the copper like water in a pipe. This is where the classic water analogy completely fails. Water flows inside the pipe, pushing directly on whatever it reaches. Electricity doesn't behave that way. In an electrical circuit, the battery or generator sets up an electric field in the surrounding space. That field extends along the wires and into the components. The charges in the wire respond to the field, adjusting their position slightly, and in doing so they help maintain the field's structure. But the energy itself is guided by the field, not carried by electrons marching forward. Feynman often used the idea of energy flow to challenge assumptions. If energy really moved through the wire, then removing the surrounding space shouldn't matter. But experiments and theory show the opposite. The distribution of energy depends on the geometry of the fields outside the conductor. In fact, if you calculate the energy flow using electromagnetic theory, you find that it streams through the space around the wire and enters a resistor or bulb from the outside, crossing the boundary from field to matter. This explains something subtle but profound. When a bulb lights up, energy doesn't arrive at the filament by traveling down the copper and crashing into it. It arrives from the electromagnetic field that envelopes the filament. The filament then converts that incoming energy into heat and light. The wire's job is not to deliver energy like a conveyor belt, but to shape the field so energy is directed where it needs to go. This idea also explains why the speed of energy transfer is so high. Changes in electromagnetic fields propagate at nearly the speed of light. That's why power systems and communication lines respond almost instantly when a switch is flipped. The field rearranges itself rapidly in space, and energy follows that rearrangement. The electrons, slow and heavy, simply adjust locally to support the new field configuration. For many people, this is the moment when electricity stops being a thing and starts being a relationship. It's not about objects traveling from point A to point B. It's about interactions spread throughout space. Feynman loved this perspective because it forced students to abandon comfortable but incorrect pictures and replace them with ones that actually match reality. The wire, then, is more like a guide rail than a pipeline. It constrains how the field can exist, channels it, and makes its behavior predictable. Without the wire, the field would spread out in useless directions. With it, energy is focused and delivered efficiently to devices. But the energy itself remains outside, in the surrounding space. Once you grasp this, many mysteries disappear. It becomes clear why insulation matters, why the shape and placement of conductors affect performance, and why electromagnetic interference can disrupt systems without direct contact. The action is in the field, not hidden inside the metal. Feynman's point was never to make electricity seem more mystical. It was the opposite. By shifting attention from the wire to the field, he showed that electricity follows clear, elegant laws. The shock comes not from complexity, but from how deeply our everyday intuitions can mislead us. Richard Feynman often said that the most dangerous thing in learning is not ignorance, but the belief that you already understand something. Electricity is a perfect example of this trap. We grow up surrounded by words like current, a flow, power, and voltage. And because we can use these words in a sentence, we feel confident. We think understanding has already happened. But for Feynman, this confidence was exactly the problem. Names are useful tools, but they are not explanations. Calling electric current a flow quietly smuggles in an image of water moving through a pipe. That image feels comforting and familiar, so the mind relaxes. Questions stop. Yet the analogy only works up to a point, and beyond that point it actively blocks real understanding. Feynman loved exposing these limits because they reveal how language shapes our thinking without our permission. When students say they understand electricity because electrons flow, Feynman would push further. Flow how? At what speed? What exactly is moving and what stays put? Very quickly, the neat picture collapses. The word flow turns out to be a label, not a mechanism. It hides the details instead of revealing them. And once the details matter, the label becomes a distraction. This is not just a problem in physics. It's a human habit. We attach a name to a phenomenon and then feel as if the mystery has been solved. Feynman compared this to knowing the name of a bird in many languages, but understanding nothing about how it lives or why it behaves the way it does. The name gives you social confidence, not insight. In electricity, this habit shows up everywhere. We say a battery pushes electrons as if it were a tiny pump. We say a bulb uses electricity as if electricity were fuel. Each phrase carries a mental picture that is partly wrong and rarely examined. The danger is not that these phrases are used, but that they are never questioned. Feynman's approach was to deliberately make things feel uncomfortable again. He wanted learners to notice when they were leaning on words instead of ideas. If you truly understand something, you can take it apart and put it back together without relying on memorized phrases. You can explain what would happen if conditions changed. You can predict outcomes, not just recite definitions. This is why Feynman insisted that real understanding feels a little fragile. You're always aware of what you don't know. You're ready to revise your picture when new facts appear. The moment understanding feels solid and final, it's probably an illusion. Electricity teaches this lesson brutally well. The moment you stop questioning your metaphors, you stop learning. You assume wires are pipes, electrons are droplets, and energy is a substance. None of these ideas survive close inspection. They work just enough to pass casual conversation and that's what makes them dangerous. Feynman wasn't trying to strip away wonder. He was trying to replace fake certainty with honest curiosity. He believed that saying, "I don't know yet," was not a weakness, but the starting point of all science. The goal was not to memorize the right words, but to see how nature actually behaves, even when it refuses to fit our favorite stories. In the end, the myth about electricity is not just about electrons or fields. It's about how the human mind prefers tidy labels over messy truth. Feynman's real demolition was aimed at that habit. Once you learn to distrust names and demand explanations, electricity stops being confusing, and learning itself becomes far more exciting.